Okay, good morning, good afternoon, good evening. Thank you all you that are attending this another nice talk today from the series of IEEE CASS talks 2021. So today we are starting a little bit early, and before giving the floor to Professors Enrico Macci and Gianvito Urgese that accept our invitation to give this talk today, I will just briefly do some announcements. So next week we have a talk by Professor José Zambuja from Federal University of Rio Grande do Sul, Brazil, talking about in-network computing and switch virtualization walking to a bar. Then November 5th is Professor Luca Benini from ETHZ Switzerland and Università di Bologna in Italy. The title is An Open Platform Approach to Low Power Computing System Design. Then I don't have the flyer yet for November 12, but November 26 is Roberta Burgi from Infinium, Germany, talking about challenge in press-silicon verification of analog mixed signal automotive products. Then next week we have also the 5th edition of the IEEE Seasonal School on Digital Processing of Visual Signals and Applications. The registration is free. You can address the webpage to see the nice program that was provided for you. Then November 16 to 19, we have the 17th edition of the International School on Effects of Radiation on Embedded Systems for Space Applications. So there is a call for poster. The deadline is next November 2nd. And you can go to the web page and the program will be available in the next days there. So we are going to have speaks from several countries around the world. It's a pity that we're not able to do a face-to-face edition this year, but next year it should be in Switzerland, in Geneva, at CERN, and then we hope that will be a face-to-face one. Also, December 13, 14, we have the workshop on women on circuits and system and the IEEE CASS meeting of the CASS Rio Grande do Sul chapter. It will be also a virtual event, so you can put in your agenda. Soon you are going to have the program. Also, if you lost the call for paper for LASCAS 22, that is the CASS flagship conference in Region 9, you can still submit your paper to the IBERCHIP workshop. The deadline is being moved to, I think, 1 week more. And also the primary A, that is the Conference for PhD Research in Microelectronics and Electronics in Latin America. Also, if you lost the CASS talks in 2020, 2021, you have the recorded sessions in this YouTube channel and much more. Some other virtual talks from other events. Now it's around 100 talks that are available there. Also encourage all you to organize your teams to participate in the IEEE CASS Student Design Competition. The first phase is at chapter level, and then you have till October 30 to do the registration of your team. Then you have the regional level, second step, where the winners of regional levels are invited to attend the finals at ISCAS that will be in Austin, May 2022. And CASS will support the travel of up 3 members of each of the finalist teams, including the trip and the hotel and so on. And then the winners will have $3,000 award also. Also, if you want to join the graduate program Microelectronics of the Federal University of Rio Grande do Sul, the submissions are open for the master and for the PhD, so you can go to that page to see more details, and there is also some scholarships available. But today we are here to attend the talk by Professors Enrico Macci and Gianvito Urgese from Polytechnic di Torino. The title you can see is The Role of ICT in the Industry 4.0 Paradigm and the Neuromorphic Technology Opportunities. So Enrico Macci is a full professor of computer engineering at Polytechnic di Torino in Italy. He holds a laureate degree in electrical engineering from Polytechnic di Torino in 90, a laureate degree in computer science from Università di Torino in 91, and a PhD degree in computer engineering from Polytechnic di Torino in 95. His research interests are in the design of electronic digital circuits and systems, with particular emphasis on low power consumption aspects. In the last decade, he has been growingly involved in projects focusing on the development of new technologies, methodology, and policy for achieving energy efficiency in buildings, districts, and cities, sustainable urban mobility, and clean and intelligent manufacturing. In the fields above, he has authored over 600 scientific publications, and Enrico Macci is a fellow of the IEEE. So Gianvito Urgese is an assistant professor at Polytechnic di Torino, where he received a PhD in computer and system engineering in 2016. He received his Master of Science degree summa cum laude in electrical engineering at Polytechnic di Torino. His main research interests are neuromorphic engineering, parallel and heterogeneous architectures, algorithm optimization in bioinformatics, embedded systems, and tool chain integration in the industrial domain. In the fields above, he has authored 40 scientific publications. He's a member of IEEE. So thank you, Enrico and Gianvito, to accept our invitation to do this presentation today. So Enrico will start speaking, and then Gianvito will do the second part of the talk. So if you have questions to Enrico and Gianvito, you can write in the chat of YouTube, and then the questions will be read to Enrico and Gianvito at the end of their talk. So now the floor is with Enrico to start. So Enrico, you have to start your sharing. So thank you very much again, and the floor is with you.
Okay, so I guess you can see my slides. So welcome anyone to this seminar. It's a very interesting opportunity. So I thank Ricardo for inviting us. Now you see the title of the talk is about two keywords which are a little bit far away one from the other, right? So Industry 4.0 means basically manufacturing processes, industrial processes, and on the other side we have neuromorphic computing. So what we are trying to do today is to build some sort of a bridge between these two worlds. In other terms, Industry 4.0 means making manufacturing processes as digital as possible. And at the basis of digitalization of industrial processes, there is information technology, and there are some enabling technologies which are ramping up these days. We believe neuromorphic technology could provide a very good help in the process of making Industry 4.0 very pervasive. Okay, so this is the outline of the talk. I'm not going to read it all. Just see that there is basically three parts. The first part is an introduction to Industry 4.0, which is what I'm going to talk about in the next 10 to 15 minutes. Then I will leave the stage to Gianvito, who will cover the part on neuromorphic technology. So he will do an overview and an insight of what neuromorphic computing means today. So we'll see what is the state of the art. And then as a conclusion, we will try to build this bridge, trying to show where neuromorphic technologies could be of very much help for the application of Industry 4.0 or smart manufacturing, call it the way you want, so digitalization of industrial processes thanks to the application of neuromorphic technologies. So this is the menu for the next 40 to 50 minutes in our presentation. So what is Industry 4.0? It's a buzzword, you go around the world and everybody talks about it, but are we sure that we are all on the same page? So do we all know exactly what we mean by Industry 4.0? Well, there is many definitions. Basically, what Industry 4.0 means is a promise of a new industrial revolution. We had several in the past. I think we are the fourth now. So Industry 4.0 tries to put together advanced manufacturing technologies, like, for instance, additive manufacturing or simulation-based design, and these kind of things, together with IoT, so that we could create manufacturing systems that are not just interconnected as they are since quite some time now, but they are also able to communicate, analyze, and use information, which is now available, in a quite large amount, to originate better processes, so better production manufacturing processes, and therefore better products. So as I said, there is a number of definitions for Industry 4.0, which is a term that was, I think it was conceived and invented first place in Germany a few years ago. So I took one from Boston Consulting. Industry 4.0 is the transformation of the design, manufacturing, operation, and service of products and production systems. So this is a very comprehensive definition, which brings in all the stages of, from conception to marketing of a product and services which are related to such a product. Now, of course, we are living very strange times this year, so we cannot avoid having a link or talking a little bit about COVID virus. And what we are observing is that actually digital technologies are playing a very important role in fighting the pandemic, and they are also playing an important role in the industrial business. So there are many companies that, thanks to the fact that they have already started their digitalization process, they have been able to face the COVID crisis in a better way than other companies that instead they were a little bit behind into this transition to the digital era. So certainly many companies had a chance to survive or at least to mitigate the effect of COVID because they could rely on digital technologies. For instance, think of companies that were able to keep operation because they could offer to their employees the possibility to work from home, so smart working, or the problems they had in reaching raw materials for supporting their production. So there are some companies that have done better in facing all these issues, and other companies that have struggled much more. And I guess there is a relationship between how the companies were able to react to the effect of COVID and what was the degree of, let's say, digitalization of the same companies. In fact, we read recently the results of a survey that was done by McKinsey by polling about 400 companies around the world. And so the analysis of the data from this survey, they brought up some interesting results. For instance, it was quite clear that the companies that were able to survive better, or even to have a reasonable, let's say, continuation of their operation during the 2 years of pandemia, were certainly the companies that had already completed their process of digitalization. So most of their operations are driven by digital technologies. Then there is a number of companies which sit in the middle. So the ones that have already started the digitalization transition, but they are not yet at the end, those had some advantages of what they were able to do, but still lacking some parts. And instead, there were a few companies in this survey that really got, a strong wake-up call from the virus. The virus said, "Hey guys, you're still doing, business as usual. Your industrial processes are still traditional. You did not do this change. You did not do this step in going towards digital technologies. Well, now we are starting paying a price." Just to give you a couple of numbers, out of the 400 companies that were interviewed, 94% said that the fact that they had digital technologies already in place in their company did have them keeping their operations alive. And more than 50%, 56% of the companies, they said that they would have not survived if they would have not had, their digital processes in place. So you see that information technology, digital technologies are really providing a very strong support to companies. So now more than ever, we need to complete this process of digital transition in the industrial sector. And this translates in a keyword, the application of the Industry 4.0 paradigm on a much, much wider basis than what has happened today. What we see is that many big companies have already done this transition, but small and medium enterprises are a little bit behind, and therefore they should actually start this process or continue this process at a faster pace. Now, what are the advantages and disadvantages and challenges of making this transition? Industry 4.0 paradigm brings in three major characteristics: adaptability, flexibility, and efficiency. So what are the advantages and at the same time the challenges that we do expect when this paradigm is actually applied? So the digital transition of an industrial sector, we expect to have an improvement, and to the application of the digital technologies to provide advantages not only to the company itself that will apply the process, but also to the players and the stakeholders which are involved in all the phases of the product life cycle. For instance, the supply chain. Okay, so we expect that a single company may go for its digitalization in the production systems, and the benefit will go beyond the boundary of the company itself. So let's try to be a bit more specific. What we do expect by the application of smart manufacturing and industry digitalization will be on the business side, for instance, shorter life cycles for the products, supply chains that may be more resilient, better opportunities to create and retain jobs. So on the business side, we expect benefits. Also, there will be an interesting process that may occur. There will be, closing of the gap between design and manufacturing production. There will be a more integrated approach to design and production of the goods, because design and manufacturing will go more together thanks to this link which is offered by the digital tools. There will be much more opportunities for data sharing. For instance, cloud will allow different plants, different companies to share data in real time. We expect a decrease in manufacturing cost, because manufacturing even prototypes or small volume products will be much cheaper than what it is happening today. And of course, since we have more flexibility in our processes and in the design, we will have most likely products that will be of higher quality and of higher complexity. Now, of course, the one we are facing now is not the first revolution in the industrial landscape. There have been several before. We are actually now facing revolution number 4. The previous one, revolution number 3, that happened in the 70s of the previous century, was basically driven by the fact that you had programmable controllers that were able to basically supervise operation of the machines in the factories. But at that time, the application of information technology was mainly manual. Opportunities for controlling and monitoring the production system was very fragmented. Data sharing was basically local to each machine or to each plant. Very low interoperability between machines and softwares, and interaction to stakeholders were basically one-to-one. Happily, with the 4th revolution, so the approach is more automated. What we have now, machines in the factories are fully automatic machines. They are fully interconnected to each other and to the production line. So there is sharing of data. There is global sharing of data also beyond the boundaries of the factory or of the company. So data sharing involves also the supply chain, and many stakeholders can have interaction all together at the same time. Now, ICT in general is playing, over time, a strong role as a game changer. I'm presenting here a couple of examples just to give you, the feeling. Think, for instance, of the market, the business of color films. In year 1998, the Kodak company was probably owning almost 85% of the market of the color film for photographs, for photos, right? And it was a company with almost 200,000 employees. Well, in 2-3 years' time, Kodak disappeared. It's under the eyes of everyone. Kodak has disappeared. And what was the disrupting, event that made this sudden change in the business of color films? Well, the advent of the digital cameras, which is a bit strange if you look at it very closely, because digital cameras came in probably in the mid-70s. But the big impact came in when digital cameras started coupling with networking, with email, with data storage on a large basis, and so forth. So a number of combos of technologies made this disruptive change to a market which was very, very stable since decades. What we are seeing today is very similar. For instance, in the transport, think of Uber. Uber is today the biggest cab company in the world, but Uber does not own any single car, because Uber is basically a software tool. So we have a cab company which doesn't own a single car. And if we go to the hotel business, same story. Airbnb is the largest hotel company in the world, but Airbnb itself does not own a single property. Again, everything, the landscape is changing so quickly and so greatly, thanks to the advent of game changers, in this specific case, information technology. So, and we are facing today, a very rapid evolution of hardware and software technologies. And there will be technologies like artificial intelligence, 3D printing, quantum computing. We expect that those technologies, which are now, ramping up and booming very, very fast, to disrupt most of the traditional industrial sectors in a time frame between 5 and 10 years. Where do we expect those impacts? Well, I put here a few examples, but of course we could be much more creative and have many more. The list is not exhaustive. For instance, mobility. The advent of autonomous connected vehicles will totally change the way people travel around the world or in the cities. The healthcare system, the advent of telemedicine services will certainly change the way the healthcare will be managed, for instance, by countries, by governments. Agriculture, the possibility of using technologies for managing different types of agriculture will make a big change, and also will make a big change in the market and in the business of entire countries. Last but not least, in my opinion, since we are university people, digital education. This has already been seen quite intensively in the past couple of years. The fact that you can offer lectures online, that you have support, digital support for lecturing, is something that may change very rapidly the way we offer education. And of course, and the pandemic has already put in evidence this point, the factory of the future, which will rely mainly on digital technologies, will be one of the sectors that will be most affected by the evolution of information technology and the diffusion, capillary diffusion of information technology. Now, in order to make sure that Industry 4.0 paradigm and requirements do find application, we need the availability of information, right information, in the right place at the right time. The world today is flooded by data. Any sensor generates data. Anyone has data available. The problem is maybe we have too many data. Data are not usable in the way they are generated. So we need to make sure that in our infrastructure, in order for Industry 4.0 to become applicable on a wide range, we need to make sure that ICT and DK enabling technologies will provide the right information in the right place at the right time. So building this infrastructure is one of the challenges in order to make sure that then the application of digital manufacturing will become reality. Now, so what are the technologies on which we can rely for deploying this new paradigm? There is different technologies. Some are quite solid and quite old, from old in quotes, of course, high performance computing, data storage capabilities, ultra wideband. Something which is a bit more recent, edge computing, cloud computing, IoT, cyber physical systems. These are technologies which are there since less time. And then there is, I just listed here a few, but we can make this list much longer, technologies which are actually, state of the art and even one step before state of the art. So I did this layering because layer one technologies are technologies which are still evolving, but they had a progress which was almost incremental in the last decade, let's say. So they are very solid technologies. They are already on the ground. We can rely on them very strongly. There are other technologies, the ones I put in layer two, which are not yet fully mature, but they had a very fast progress at a very fast pace in the last decade. And then, as I said, layer three, most of the layer three technologies are currently having a boom, and therefore they have a great opportunity for very fast progress in the next decade. So many of those technologies could find a way into the implementation or as a support of the implementation of all the requirements of the Industry 4.0 paradigm. So the factory of the future certainly will feature smart and connected systems to support the monitoring of the production, the control, the optimization, the automation of the entire life cycle of the products. Neuromorphic hardware and software will play an increasingly important role in the as enabling technologies for edge computing, IoT, robotics, machine learning, and so forth, which are at the basis of the implementation of the Industry 4.0 paradigm. We believe that neuromorphic computing will be one of the keys for what will be the deployment of I4.0 in the next 5 to 10 years. So what we're going to do now is to take a quick but reasonably detailed look at the state of the art of neuromorphic hardware and software. So at this point in time, I leave the stage to Gianvito for continuing the presentation. Thank you very much.
Thank you very much, Enrico. Can you see me? Okay, perfect. So let's I will start this next part of the talk from a simple analogy that helps in figuring out what are the major advantages of using the biological brain when compared to the standard computing technologies in implementing complex tasks as flight control. Here, the comparison is between a small parrot and a modern drone. A drone today is able to fly at standard speed, avoiding obstacles thanks to the computer vision, but it is limited to increase the speed further because the latency into the control flow between sensors, processors, and motors. Standard methods of execution involves a latency that can be fatal during the autonomous flight. Images detected by cameras take a few milliseconds to be transformed into the control to be given to the engines. But not only that, the processing of machine learning models and the analysis of the amount of data arriving from the sensors also require considerable effort to the processor, which turns into high consumption modality. And finally, should the flight condition change, the drone is not always able to adapt since its flight style is conditioned by the set of instructions contained into the model. The parrot has a totally different behavior. It has a small brain weighing a few grams that burns few calories, yet it manages to avoid obstacles much faster than the drone and goes faster and also adapt to changes condition, guaranteeing high level of performances. So for the parrot, it is unlikely to hit an obstacle. The difference is simple. The parrot's brain thinks asynchronously, quickly, receives stimulus in some areas of the brain, and reacts to those stimulus by parallelizing the instruction. The drone processor performs the calculation in a pipeline, and this leads to an increase in latency and consumption. From this simple example, it is evident that we need a new brain-inspired computing paradigm to port on the drone some of the advantages of using the parrot brains. So, and basically this is the principal goal of the neuromorphic engineering field. So here we show a possible scenario of a future smart manufacturing system with different systems orchestrated to collaborate into the production line. Here, distributed agents are equipped with sensing, computing, and actuation capability, or a subset of thereof. And dependingly on the manufacturing task at hand, which can change dynamically at runtime, the agents interconnect wirelessly to form teams within an automation cell, among cells across the factory hall, and with global wired communication infrastructure to access, for example, the cloud services. So as we learned into the previous section, the implementation of the Industry 4.0 paradigm can be realized by integrating the different technologies to develop and use smart connected systems which enable new categories of capabilities for monitoring, control, automatize the life cycle of the products. Today, autonomous systems elaborate many sources of inputs with sophisticated and self-learning algorithms for analyzing system performances and environment to react to conditions in real time. Moreover, autonomous systems act alone or coordinated with each other. And someday, we will have smart factories where smart connected machines produces other smart connected products, reducing the human effort for routinely and not creative activity. In this direction, as we learned from the parrot example, the usage of brain-inspired technology could speed up this transition. So although into the original definition, the terms neuromorphic was restricted to the set of analog VLSI circuits that operate using the same physics of computation used by the nervous system. For example, silicon neuron circuits that exploit the physics of the silicon medium to directly reproduce the biophysics of nervous cells. The definition has now been broadened to include analog digital hardware and software implementation of neural processing systems, as well as spike-based sensory processing systems, who communicate asynchronously. This is one of the important, let's say, features that characterize those systems. So a neuromorphic computer is a computer whose underlying architecture and the way that it performs computation is inspired by the biological brains. Heterogeneous teams interact for study and develop several aspects of the neuromorphic computing technology. The interaction can be read in both directions. From left to right, biologists study the biological mechanisms and create models which are used by computer scientists for implementing bio-inspired algorithms on which are based the specification for the development of new devices capable to support those algorithms also by using new materials. On the other side, new materials enable new properties for the devices so that computer scientists have new exploration dimensions to exploit into the implementation of algorithms, and together this system can be used by a biologist that can have benefits in validating in simulation what they have observed into the nature. So this win-to-win approach has been at the basis of the Human Brain Project work, where engineering teams had the chance to study and develop new, more power-efficient systems, with neuromorphic learning capability for defining more efficient computational paradigms. On the other side, scientists exploited the hardware architecture and the brain simulation frameworks to validate mechanisms of brain computation, memory, and cognition in controlled simulation experiments. So before moving on, we need focus on things to know about the brain. So the brain is soft, is three-dimensional, grow during the life and not built. It changes with time for allowing learning and forgetting. It works with electrical spike and chemical signals, act at various length and time scale at the same time. It implements sparse and low frequency communication systems and never switch off. So the human brain has about 10 to the power 11 neurons, and if this would be mutually interconnected, this would result in 10 to the power of 22 synapses. That is an unimaginable number of for which there is simply no physical space into the head. Indeed, the neurons in the brain are densely interconnected at the local scale and gradually more sparse for long-distance connections. So then moving on, in this slide and in this section, we make a side-by-side comparison between animal brain computing architecture, von Neumann computer architecture, and the neuromorphic architecture, and how deep learning computing can be executed on the hardware architecture for the sensing and device to the algorithm levels. So in a brain-like neuromorphic computing system, devices, computing and memory units need to be replaced from traditional CPU and SRAM to artificial bio-inspired electronic neurons and synapses. And this is the first step for mimic the brain at device level. So unlike computing units in the CPU that performs the binary code-based computing, the data in electronic neurons and synapses need to be represented in a spike sequence format for generating the brain-like signals. Then these electronic neurons and synapses are interconnected with each other in a brain-like neural network configuration at the architectural level. Spiking signals are used to communicate in this architecture, thus encoding spatiotemporal information instead of the real values needed to represent time or space into the deep learning networks. So in this slide, we give a demonstration of spike encoding. Here we have same data as spatially and temporally arrangement. And as we can see, spatial data is encoded by associating an input neuron to each pixel of the matrix, which encode the value into the time domain. While temporal data is encoded directly in a stream of spikes from a single input neuron. So spiking neural networks are mapped on the distributed processing cores and memory resources available on the neuromorphic architecture, which support fast communications of small packets representing the spikes. So the neuromorphic architecture eliminates the long signals transferring distance between CPU and the memory that is standard for the von Neumann architecture, since the computing can be performed by neurons with the data extracted from closed memories simulating the synapses. So due to the unique non-von Neumann architecture and the spiking encoding scheme of the neuromorphic computing system, the binary algebra is not suitable for this system anymore. So in the field, neural network-based machine learning algorithms are widely considered as the ideal candidate for running neuromorphic computing system, even if several big differences exist between deep learning techniques and the neuromorphic computing paradigm. So deep learning works with information encoded in real value, while neuromorphic computing uses discrete spike and precise timing. So in the deep learning, learning rules are global and require floating point precision, On the other side, neuromorphic computing is suitable for local learning rule, where weight updates is possible with limited precision. Deep networks are synchronous and built with relatively homogeneous architecture of simple components, whereas neuromorphic networks work in asynchronous and have a huge diversity of cell types and connectivity patterns. So all these differences because neuromorphic computing is inspired by the animal brain. Indeed, when we compare the animal brain and the deep learning features, we discover several advantages offered by the problem solver system evolved during the millions of years. Indeed, animal brain is developed into the embryo from a single cell through neurogenesis and plasticity mechanisms, not requiring manual configuration as deep learning needs. It balances the stability of memory with the adaptation need, not suffering for catastrophic forgetting. It is capable to learn from few examples. It is resilient to small input changes, adaptive to internal changes. It works in multi-scale dynamics and never stops the activity from birth to die. And very, very important, consumes only 20 watts of power. So although algorithms of the brain are still under investigation, two main elements, neuron and synapses, are well studied at the cellular level. There are four main parts of each neuron, whose functionalities are summarized as dendrite, that is the input, and is the organ that receives spike signals from other neurons. Then there is the soma, that is the cellular body, that generates and sends spike signals to the axon if the integration of receiving spiking signals exceed a specific threshold voltage. And then there is the axon that propagates spike signals to other neurons. Then we have the synapse, that is a space between the axon of the presynaptic neuron and the dendrite of the postsynaptic neuron. And this is widely considered as the memory organ in the brain that works by storing the memory information in its connectivity strength that is proportional to the dimension. So in biology, there exist many types of neurons localized into different regions of the brain, which are specialized to perform specific tasks associated to that brain region. So the typical behavior of a neuron is to accumulate charge through a change in voltage potential across the neuron cell membrane caused by receiving spiking signals from the input neurons. Then the voltage potential in a neuron may reach a particular threshold, which will cause the neuron to fire. That means generate an action potential that will travel along the neuron axon to affect the charge of other neurons through the synapses. Most neuron models implemented into the neuromorphic systems have some concept of accumulation of charge and firing to affect other neurons. But the mechanisms by which this process takes place can vary significantly from model to model. We have more complex models and less complex models. So concerning neuromorphic sensors, we have several technologies which take inspiration from the animal senses. The most successful at the moment is the silicon retina, also known as event camera, that is a novel sensor that measures only the motion into the scene, discarding the fixed background. It offers low latency, no motion blur, high dynamic range, and ultra-low power capability. And this is particularly useful to avoid post-processing of images to remove the static background and for reducing the sensor-to-processor bandwidth, since only informative pixels will be detected and transmitted. So after this side-by-side comparison, we can focus on some of the most important hardware architectures widely used into the neuromorphic community. So neuromorphic hardwares can be categorized into three main types: analog, digital, and mixed, which offers several different features such as programmable architecture versus custom chip, degree of parallelism, general purpose versus application specific, on-chip or off-chip learning, they can manage different input types and they implement different communication networks. So here we have a first example of neuromorphic architecture called Spinnaker. Spinnaker is a massively many-core, globally asynchronous, locally synchronous architecture designed by the group led by Professor Steve Furber at the Manchester University. And here we have the Spinnaker chip that has 18 ARM cores, an hardware router, and an interface to 128 megabytes of external SDRAM. Here, all the cores are identical and designed for running neuron models simulated in software. So the Spinnaker chip are assembled in a Spinnaker board that is a PCB that hosts 48 nodes placed in an hexagonal-shaped triangular mesh. And basically, this structure allows each node router to communicate with its own 6 neighbor chips in order to, let's say, allows the implementation of the full toroidal. So the board hosts 3 FPGAs, which are used for board-to-board communication, and this allows to connect many boards when are put together, they form a sub-rack shown here on the right, and when those sub-rack are joined together, they can produce the full system that is currently hosted in Manchester, that is built with 1 million cores. So the first release of Spinnaker architecture have been released in 2013 at the beginning of the Human Brain Project, and currently a new revised and upgraded version is going to be released under the name of Spinnaker 2. This new version is again a multi-processor system on chip. This time we have 122 ARM-based processing elements, 4 GB of DRAM. Then we have a dynamic power management system. We have several neuromorphic hardware accelerators and an ARM Cortex M4 microcontroller that, let's say, give more flexibility for the interfacing with the digital world. Altogether, this new version of Spinnakers makes the platform more general purpose and customizable for several IoT and robotics applications, which are believed to be the ideal candidate for this platform. So then from 2017, Intel have created a neuromorphic division which have developed a neuromorphic processors that is called LOI. LOI is built with 128 neuromorphic cores supporting up to 128,000 neurons and 128 million synapses with an advanced spiking neural network feature set. It supports highly complex neural network topology. It is scalable. It supports scalable and on-chip learning capability to support a wide range of learning algorithms. It is a fully digital asynchronous implementation fabricated in a 14 nanometer FinFET process technology. So the 128 neuromorphic cores work in asynchronous and implement a particular neuron model called Leak Integrate and Fire, where parameters can be customized. So differently from Spinnaker, here the neuron model is fixed. It cannot be changed. Only configuration parameters and the network topology can be configured. It implements a low overhead NOC fabric for supporting the intercore communication and hosts 3 embedded x86 processors for interfacing the neuromorphic system with the digital world. So in the beginning of October, a new version of Intel OE have been announced by Intel, supporting several new features requested by the neuromorphic community research teams for supporting the state-of-the-art models. And in particular, it have now 8 more times neurons and 2 times more processors, together with a more flexible instruction set that will allow to, let's say, customize more the neuron models. So then we have several other neuromorphic architectures that are emerging, and here in this slide we report just 4, but many others are available today. Each of them have several particular features. Some of them are more, let's say, proper for low power applications. Some of them for accelerating the simulations. Some other one are more, let's say, flexible than some other one. So an important aspect to be considered when selecting the neuromorphic architecture for implementing a particular use case is the degree of programmability offered by the platform. In platforms emulating a particular neural model, only parameters of the models can be configured, while more general-purpose platforms simulating the neurons allows fine customization of models and connectivity. Of course, more general-purpose architecture like Spinnaker are less efficient in power consumption if compared to custom analog chips with fixed neuron models, like, for example, DNAPCell. So, impressive progress on the hardware side are not followed by the development of software frameworks, which continues to hold back the field. Over the past several years, there hasn't been an emergence of a single software framework, as we have seen into the deep learning world, where we have TensorFlow and PyTorch that support the users in the development of deep learning algorithms. So thus forcing the different teams to develop their application with custom self-made scripts difficult to be shared in the community. So currently we have PyNN and Nengo that are widely used, even if several important features are not universally supported. And to overcome this bottleneck, Intel proposed recently a software framework named Lava, designed to address many of the weaknesses of the other available frameworks. So at this point, it's useful to ask ourselves what are the appropriate applications for the neuromorphic computing paradigm that can be exploited into the industry domain. So as we will see into the following, some of the application fields have been already considered in several research work, in particular using the hardware neuromorphic processor as coprocessor, application on large-scale data analytics, on cybersecurity, on autonomous vehicles, robotics, Internet of Things, and smart sensors. So in these domains, three different types of applications have been investigated. Neural network-based applications for event-based sensing, classification, control, and other machine learning tasks. Then we have engineering applications for solving constraint satisfaction and optimization problems, implementing graph algorithms, and solving pattern matching tasks. And then we have biological simulation for testing what have been observed into the biological brain. So even if the perimeter is of the proposed applications have always been constrained by the weak development status of supporting software and development frameworks which do not support properly a wide range of standardized and cross-neuromorphic platform computational primitives. So in this slide, in this last part of our talk, we can explore with concrete examples how the neuromorphic technologies can be exploited in an hypothetical industrial production line to form hybrid digital neuromorphic systems, enabling the next generation of artificial intelligence that will help us in overcoming the challenges of the Industry 4.0. So in these first applications, author have designed a neuromorphic model inspired by the Sun Scorpion to explore the benefits of temporal coding and validate it in an event-based tactile sensory processing task. So the task consists in localizing and estimating the distance of target object, which emits vibrations using only the relative spike timings of 8 spatially separated vibration sensors. So in this application, the spiking neural network learns to cluster the spatiotemporal patterns in an unsupervised manner, demonstrating how the task can be solved through the simulation of multiple spiking neural networks models. The spiking neural networks uses the precise timing of events detected by the sensors to learn in a purely event-driven manner, which have been demonstrated to give advantages to reduce the power consumption of the task, since the system is called to react only when an input is presented, instead of continually monitoring the sensor's outputs. So this neuromorphic application can be of inspiration, for example, into the industrial domain for the development of always-on collision avoidance systems able to detect position and distances of moving robots with small requirements of energy and computational resources. So to design low power system for monitoring the health conditions of a boiler case, for example, in order to identify microcracks that can compromise the structural integrity, or the development of real-time monitoring system to detect the presence, absence, and the exact locations of pieces dropped on the assembly line. So in this second application, Blow et al. Have designed a keyword spotter network implemented in TensorFlow and running on several different devices. A CPU, a GPU, an NVIDIA Jackson TX1, the Intel Movidius platform, and the spiking version running on the Intel OE Neuromorphic platform. So here, on all the devices, audio features are passed to the input layer, and the probability distribution over characters are read from the output layers, ensuring that identical amount of computation are performed across all comparisons. So as we can see in the plot, neuromorphic solution provides a 5 to 10 times lower energy consumption than closest conventional deep neural network architecture for real-time inference, while maintaining equivalent inference accuracy. So the extremely power-efficient performances of this second application could be exploited for the design of human-machine interface for voice control of machine operation running on portable device, which require to work with batteries for a long time, or for the implementation of on-edge continuous audio monitoring system for detection of dangerous condition for the human health, or for implementing detection of audio signals in a noisy environment associated to faulty operation of running machine, and is for predictive maintenance purposes. So moving on, we have two different works where authors demonstrated the basic principle of stochastic spiking neural network-based framework by solving difficult instances of the Sudoku puzzle, the map coloring problem, the easing spin glass, and the traveling salesman problem. So here the solver works as a stochastic dynamical system, which is attracted by the spiking neural network configuration that solves the constraint satisfaction problem. Here the noise in the network allows an optimal exploration of the space of configurations and looking for the stability of all the constraints. So a recent report on an implementation of Intel OE show an improvement of 100,000 gain in energy delay product compared to the conventional solution. On the same neuromorphic platform, has also demonstrated how the computation of train scheduling can be accelerated up to 14 times while reducing the power consumption by 2 to 3 order of magnitude. So on the industrial side, this neuromorphic optimization algorithm can be exploited for implementing, for example, accelerated scheduling of tasks and materials in the assembly line of a smart factory for optimizing the supply chain, or for implementing low power optimization of path planning in continuous space for autonomous vehicles like drones or robots. So recently, a couple of teams have implemented a neuromorphic version of proportional integrative derivative control, able to outperform conventional control paradigms in terms of robustness to perturbations and adaptation to varying conditions. This paving the way to a fully neuromorphic system in which perception, planning, and control are realized in a non-chip spiking neural network, and thus avoiding expensive digital-to-spike encoding decoding procedures. So obviously, these solutions could be really useful in the industry, for example, in enhancing robotic arm control, increasing the drone stability and navigation controls, and many other control applications that are really useful into the industry domain. So neuromorphic systems for real-time anomaly detection uses analog sensors inputs which are converted to event trains and processed by a spiking neural network on neuromorphic processors. So for each type of anomalous patterns, a readout unit filter neurons firing activities to estimate the likelihood of an anomaly in the input signal. Then a binary output signals indicate whether any readout unit crossed its detection threshold. So this pipeline has been successfully applied on two types of inputs, electrocardiogram and accelerometer vibration, on the custom analog DNAP cell chip, and the proposed method achieved state-of-the-art or better performances on publicly available datasets while reducing the power consumption. And basically, this represents a significant step towards autonomous low-power edge computing devices for biomedical and industrial applications. So in industry, continuous monitoring of motors and environmental conditions are really useful for triggering, for example, predictive maintenance activities, reducing the stop time of the production line. So here in this slide, we have the last application where authors have designed a neuromorphic method for training an event-driven classifier with a spiking neural network system. This yielding good classification results when using video and audio signals captured into the spike domain with neuromorphic sensors, which have been demonstrated to be low power, really fast, and with modest bandwidth requirement because of the event-based working mechanism. So in the industry, silicon retina and silicon cochlea could provide distributed ACE and AIRs in the factory. For example, to implement high-speed and low latency visual monitoring of quality and integrity of pieces produced into the additive manufacturing process, for fast recognition of identification number of products moving on the assembly line or factory environment, and for the anomaly detection of machines from changes into the sound and vibration patterns during the operations. So as we see in this list of applications, this hybrid digital neuromorphic systems will allow animal-like sensor system, for example, ACE, tactiles, and AIRs, to detect signals from the physical world and transform them into spiking signals for the cyber-physical systems and Internet of Things. Animal-like control techniques adaptable to continuous changing condition for driving actuators in noisy environments, and animal-like learning methods enabling a digital neuromorphic system to learn from environmental condition and previous experience to solve optimization and pattern matching problems in Industry 4.0. So what is the identikit of the technology of the Industry 4.0 that can have huge benefits from the adoption of the neuromorphic technology? So neuromorphic computing allows solve hard problems quickly for search and optimization, real-time pattern matching, graph analytics, scientific computing. It enables the implementation of novel artificial intelligence algorithms. It can support online adaptation and learning, is usually applications can work well in real time with low power and low latency temporal data processing. It enables order of magnitude lower latency and power in event-based sensing, but this at the cost of rethinking visual, audio, and tactile sensing. So from what we have seen in the different application examples, we can expect an important contribution of the neuromorphic technology into the edge computing domain, where systems need low latency between data analytics steps for implementing low-power autonomous systems. But also several other technologies could have benefits from the exploitation of neuromorphic systems to be coupled to the standard digital technologies. So moving on, we can take a quick look at the trends in scientific production of neuromorphic engineering works. As we can see in the slide, in this field, there is a constant increase of papers produced per year, and today reaching almost 30,000 in total. And this is an important warning, showing that this technology is growing day by day and closing the gap between purely academic study and the adoption into the industrial use cases. So from the market size perspective, a recent report evaluated the global neuromorphic computing market size at $1.49 billion for 2024, with application in several industrial sectors as consumer electronics, automotive, healthcare, and military. And here we show the companies currently interested in producing and adopting neuromorphic solution for their products. As we can see, there are already several stakeholders in the domain who are able to produce neuromorphic chips, supply algorithms, sensors, and devices, which can be used to develop new smart connected neuromorphic products and solutions to be launched on the market. So to conclude, earlier in this talk, we said that in Industry 4.0, we need to standardize the tools and the adaptation of the integrated circuit technology. The path towards more and more neuromorphic technology being adopted into the industrial domain is the same. We need new standard tools for the development of hybrid digital neuromorphic industrial applications. A significant amount of work has been done already in building neuromorphic hardware and systems over the last few decades. A wide variety of models, algorithms, hardware devices, and applications have been explored. However, we have barely scratched the surface of what is possible within the field of neuromorphic computing. So significant work is left to do in the algorithm and computational paradigm development. Now more than ever, the focus should be on the design of integrated software frameworks that can support developers in adopting neuromorphic solutions during the design of applications and systems. So, and this basically concludes the really wide overview that I would like to share today.
So thank you very much, Gianvito and Enrico. So now it's time for questions. So if anyone has a question, please write in the chat channel. So the first one is from Thalita Borges from Federal University of Rio Grande do Sul. Are the algorithms using neuromorphic computing seek to imitate the behavior of neurons? Does this require knowledge in medicine?
Not really, because usually what's happened is that you have your algorithm is implemented on the way you build your network, and the neurons can be customized, let's say, with some knowledge of what works better for the application. So usually you have models of neurons that are not, let's say, strictly simulating what is available in biology. For example, the leak integrate and fire is a neural model that really approximate the biology in a really high level, but let's say the function that implements let's say that for answer to the question, we can say that you don't need to really have a big experience into the biology for using these technologies. Let's say like this.
Thank you. So now a question by Cristiano Chenet, also from Federal University of Rio Grande do Sul. Thank you, Professor Enrico and Gianvito, for this wonderful explanation. Please, could you comment on what Neuromorphic could teach to improve the performance of the testing of electronic systems? There is a second part. For example, is there something based on Neuromorphic that an engineer at the industry, for example, at a cell phone line test, could implement to improve test cost, time, accuracy?
So,
well, I would. Okay. Bye.
So what I see is that usually, let's say, you can use when you think about the neuromorphic architecture, you can think it, let's say, as a coprocessor to be coupled with a standard digital system. And so the neuromorphic systems are not, let's say, conceived to replace the digital world. They are conceived, let's say, to improve the solution space available when you build a complex system of systems. So you can have you can consider them as a hardware accelerator to implement specific tasks. In my view. So Enrico,
yeah.
Do you
So
want to...
in the specific, if in your system where you do chip testing or phone testing or whatever, if you have some tasks which require, for instance, data processing, which is particularly intensive, or some running some AI algorithm, machine learning algorithm, which is particularly difficult, you may think of having a coprocessor, which is a neuromorphic coprocessor, which then interacts with the, let's say, traditional or standard machine that you have for the testing. So basically, you try to take out from the mainstream computation some difficult tasks and have them implemented with a coprocessor, which in this case would be a neuromorphic coprocessor.
Exactly.
Just to give you a further example, the human brain project that we are working on, in fact, it is using a combination of computing systems to emulate the behavior of now of animals. Of course, we are not yet at the human brain model, but there is a supercomputer by IBM which is doing most of the work. But then there are some tasks which are very suitable to, computations which are similar to what synapses do in the brain, and therefore those tasks are implemented by means of neuromorphic hardware in parallel or in conjunction with the supercomputer, which does most of the work, the traditional work.
Okay, thank you. So a question by Professor Thiago Weber. In hardware limited edge devices application, as in many industry cases, do you consider less computational intensive machine learning algorithms could be the way to go in some cases in Industry 4.0, like decision trees?
So in my opinion, if the direction is to, let's say, to have a production line tightly where machines are tightly connected each other, we cannot just rely on the cloud computing, because we have always the bandwidth limitation and the time needed for upload and download the information that have been computed, let's say, on demand. Let's say that these neuromorphic technologies will be really useful for the automatic connection between the different machines on the production line, so that several tasks can be, let's say, implemented directly in situ without, let's say, moving the task outside. And so this will allow us to have more intelligent algorithm directly on the field, because of the extremely because of the different properties available with these new technologies.
Thank you. So now a question by João Carlos Brito Filho from UFRGS. In your opinion, is there the possibility of using neuromorphic technology to improve the consumption of virtual helpers in applications like Google Home and Alexa, or in seek-to-seek model, example, chatbot?
In case you apply in the systems also a coprocessor with neuromorphic capability, this will be, let's say, available directly on the device, and this will also address another issue of the privacy, because then you can, by having the intelligence directly on edge, then you can avoid the transmission of sensible data to the cloud. And so, yes, I think that if in the future, if the neuromorphic coprocessors will be coupled directly on the same chip or on the same system as have been already done for other accelerators, this will give benefits for let's say, for implementing this new task.
And in terms of power consumption, certainly, well, it depends on what kind of algorithm you want to implement on a neuromorphic platform, because power versus comparing power by the neuromorphic computer versus the power consumed, for instance, by a traditional processor-based architecture, well, it depends on really what algorithms you are running. So in some cases, if the algorithm is very suitable to neuromorphic computation, certainly the computation, for instance, a lot of asynchronicity, then you would have much advantages on the neuromorphic platform. If instead it's continuous computing, where you do, it's almost a synchronous algorithm, then I'm not sure there will be so much of an advantage, because you will have to keep the neuromorphic architecture running all the time. So the fact that it is an asynchronous model, it helps when you have idles versus computing times. If it's continuous computing, I'm not sure what is the advantage. So it really depends on the type of application, on the type of algorithm, for both performance and power consumption.
Yeah, for what we have seen today, for example, if you have the constraint satisfaction problem, this can have benefits in being solved with this technology, and this is, let's say, a task that you can call directly on edge if the neuromorphic if on the system there is neuromorphic availability. Of course, the majority of the applications exploit the neuromorphic hardware in continuous monitoring, because you have an event-driven approach at the task, and so basically is low power. Let's say is more natural to be low power for an architecture such that.
Thank you. I see no more questions in the chat. I have a final one. If you can comment, if you have some information about the neural processing units that we can find in the Apple processors nowadays. Hello?
Sorry, I lost the audio. I lost the audio for a second.
Are you hearing me now?
Yes, now yes.
Yeah. My point is, if you have any comments or information about the neural processing engines that are included in the Apple processors nowadays.
On the Apple processors?
Yes.
So you mean the
NPU, the neural processing units?
Okay. So I didn't study well this architecture. For now, my experience was more into the direction of let's say of devices that are available into the neuromorphic field. Let's say LOE, Intel LOE, or Spinnaker, or Brainscale S, DynapCell. The Apple processor was not, let's say, was not into the interest of the neuromorphic community at the moment, for what I see.
Okay, so I think I see no more questions. Some congratulations here. So thank you very much, Enrico and Gianvito, for this very nice presentation, a hot topic. I hope to
Thank you, Ricardo. Thanks for the invitation.
Thank you to accept our invitation. I hope to see you in person in a near future.
Absolutely. Yes.
Okay.
Okay.
So thank you very much. Bye-bye. I will just remind people about next week. So next week, the next CASS talk will be with Professor Azambuja, and it will be the traditional hour at 1:30 p.m. in Brazil. And it will be about in-network computing and switch virtualization walk into a bar. And if you want to see the other talks that are scheduled till November, you can see them in the YouTube channel, as well the recorded version of past talks done in 2020 and 2021. So thank you all the attendees for joining us today, and thank you Enrico and Gianvito for this nice presentation, and thank you very much again. Bye-bye.
Bye-bye.
Bye-bye. Bye-bye.